Now, the last thing for today, we will look at the intensity distribution of the radiation as a function of frequency, and frequency is related with the photon energy of the emitted radiation, and that is the thing we can compare the actual spectrum with observationally from the actual data. So what we have at hand, we know that the power emitted per Salt angle, that is equal to C over 4 pi R square E square, and we can write this in general by defining some vector A, and that some vector is, let's say, as a function of t, C over 4 pi square root of 2 R times E. So then the power emitted per Salt angle is nothing but A square, which depends on time. Now, that is the energy per second per Salt angle. So if you integrate this through the all possible times, we obtain the energy per Salt angle, and that integration is the following: A of t square dt from all time intervals. So why we did this? Because this integral could be expressed in terms of the in the frequency domain using the Parseval's theorem. So let us define the Fourier transform. So if you know that the A of t, you can have the Fourier transform if you integrate this all time intervals times 1 over square root of 2 pi will give you the Fourier transform of this. So if you have some quantity in time domain, you can express in the frequency domain by using the Fourier transform, or you can define like the inverse of this. E of t is 1 over square root of 2 pi from minus infinity plus infinity the Fourier transform of the A integrated through the all frequencies. Now the exponent is the negative of the previous one. So you have the Fourier transform and inverse Fourier transform. Our aim is the following: we have the power emitted per Salt angle, so in the original definition, and that is related with the electric field, and the electric field is depending on the time in general. And basically, if I call that the A vector as a this, and the power emitted per Salt angle could be written as absolute square of the A of t. Now I will try to convert this integral to the frequency domain. Then I will express that the intensity frequency spectrum of the emitted radiation in general form, and next week we will do some applications. So the energy emitted per Salt angle is the A magnitude square integrated all the time intervals. Then you can write this in the following form. You can use that you can write this minus infinity plus infinity A of t complex conjugate dot A of t integrated all times intervals. And if you take this and plug it there, you will have the following. So A and A complex conjugate of T will have 1 over square root of 2 pi, and once more of that will be 1 over 2 pi. And what else? We have the dt integral for all times, and we have the frequency integral, and we have, let us say that the A of t could be written omega, or A of t complex conjugate written as a omega prime, A of t written in terms of omega. We should use a different indices for the integrations, otherwise everything will be mixed up to each other. Then we will have A complex conjugate of omega prime dot A of omega, and if you have the complex conjugate of this, you will have plus I omega, and omega is omega prime, and you have the dot product with the A omega, and let's say this is the omega, and then you have the exponent in the following form: e to the I omega prime minus omega t. Okay, so these are the same things. Instead of A complex conjugate t, I used the inverse Fourier transformation of the A omega, and A omega is expressed as omega prime, and instead of A t, I used the Fourier transformation of the A omega and substitute there. So basically I am deriving quickly the Parseval's identity. So power emitted per Solt angle, so energy emitted per Solt angle, not the power, energy emitted per Solt angle, could be arranged in the following form. So 1 over 2 pi here, and take the omega and omega primes integrals in front, d omega prime, and we have A complex conjugate omega prime dot A omega, that term, and take the first time integral. So take the first time integral dt, and e to the I omega prime minus omega t. So if you plug this 1 over 2 pi here, this is all together integrated all time intervals. This is all together is nothing but the definition of the canonical delta omega minus omega prime. So then if you take the integral through the d omega prime, instead of omega prime you will plug as a omega, and you will obtain the very nice definition that tells you that power emitted per Solt angle evaluated in the time domain A of t square is equal to the frequency domain integral A of omega square d omega. So that this is nice because omega is related with frequency. Frequency, if you have the frequency spectrum of the radiation multiplying with the Planck's constant, you can have the energy spectrum. So this Parseval's identity is very useful, and the definition is the following. So let us take this piece and rewrite everything. So this is a very nice result, because we will do the following: d omega over per Solt angle, omega again is the energy per Solt angle, is equal to minus infinity plus infinity a omega square integrated through the all Solt angles, and we will write this in the following form. We will call this in the following form. So one thing I have to tell you that this is minus infinity plus infinity means that minus infinity to the 0, 0 to plus infinity, but this is an even function. Fourier transform, square of the Fourier transform is a even function. That means that this is equivalent to 0 times infinity, 0 to infinity times the 2. So basically, we will write this all together 2 times. So we will write this as a 0 to infinity d square of energy per frequency radiated along n hat direction per frequency per salt angle. So this will be the format of this. And this is equivalent to 0 to infinity 2 times of this. Okay, from instead of minus infinity plus infinity, write 0 to 2 infinity times 2 types of integral. And the definition of this, is it the correct definition? Because if yes, it is. If you integrate this function, you will obtain di over d salt angle. I is nothing but the energy. So this is called, this whole called stuff here is called energy radiated per unit solid angle and per unit frequency. Now let us look at the radiating fields and try to put the things in more compact form. So this is the general expression. So basically the situation is the following. The situation is the following. If I know that the A of t, then I can calculate the A of omega. That means that I know that the intensity distribution is a function of frequency. D square of radiation along the direction of n per salt angle per frequency is equal to 2 times of what? 2 times of A of omega square. If I know the electric field is a function of time, then I can take the Fourier transform. That means that I will have the intensity spectrum. We can compare that the intensity spectrum as a function of energy versus intensity with the observational data, which could be done for the Bremsstrahlung emission, cyclotron emission, also Cherenkov radiation. But I want to go a little bit more work before to discussing the physical processes. I will discuss the physical processes next week. Now let me continue with the calculation of the A of omega for the fields of the moving and accelerated charge. So basically, I know that the definition of the Fourier transform, and I know that the fields of the moving and accelerated charge. So then A of t will be what? A of t is equal to c over 4 pi 1/2. Okay. And r times I need the fields of the accelerated charges. Do I have, or I can write here, that is E over c 1 beta cross beta dot divided by 1 minus beta dot n cube r. Okay, r's will be cancelled. And this coefficient takes the what? E square in, the square root of 2, c square in, and that will be what? 4 pi square over c 1/2 from minus infinity to plus infinity I omega t and cross n minus beta cross beta dot 1 minus beta dot n cube. So this will be the all expressions. Yes.
Because pi square.
Maybe we don't have the pi square, so we have the definition of c over 4 pi square root of, and this should be in that form, I think. So this should be e square over 4 pi c. Yeah. There's something wrong. Yes, that should be 4 pi. So that's correct. So you look at the definition of the Fourier transform. Fourier transform has the what? A of omega. A of omega is 1 over square root of 2 pi minus infinity to plus infinity a of t plus I omega dt. So we have 1 over 2 pi. So if you have square root of 1 over 2 pi, this term, then you will have what? This goes as 4 that should be 8 pi square. This should be 8 pi square. Okay, so we have the 2 pi factor, square root of 2 pi factor from the Fourier transform of the definition. Thank you. I also confused a little bit. So today I will put this integral in a nice format, and next time we will do the applications. A of omega. So do the following thing. Instead of t, write the dt prime and dt prime. So this should be taken through the what? dt and dt. So let the t prime plus r of t prime over c is t. As usual, the charge is moving. This is the location of the charge. This is our point of interest. When the radiation emitted, when the information reaches to the observer, charge is not this point, it is somewhere else. So the location of here we can call x prime and t prime or ct prime, and here we can call x ct, and this length is r. So x minus x prime vector has the length of r, and r is depending on t prime. So basically this is the t observed here. The radiation emitted at t prime propagates a length x minus x prime magnitude with the speed of light in the vacuum. So again, like we did in the previous case, we can write this, using this, we can write dt prime 1 minus beta dot n dt. I am not doing the same things again and again. And we can convert the integral to the following format. So basically, instead of dt, I can write 1 minus beta dot n dt prime. And instead of t, I can write t prime r of t prime. So let me write one more. Let me write one more this whole stuff here. So instead of t prime, let me write the in terms of t prime. So we have e square over 8 pi square c 1/2 from minus infinity plus infinity e to the plus I omega t prime n cross n minus beta cross beta dot. One of the terms will be cancelled, this one, and divided by 1 minus beta dot n integrated dt prime so sorry, this is omega t, this is omega t. Now instead of dt, I write 1 minus beta dot n dt prime in here, and instead of t, I should write t prime plus r of t prime over c. So this term is nothing but t. Then we can do one more trick here. The trick is the following. If I look at the radiation in the far fields, suppose that this is the charge location is somewhere else is locating, and this is the charge location x prime, and if this is our point of interest, so then we can write that so suppose that the charge is locating somewhere else locally, and then x minus x prime is this vector, and the magnitude of this vector is approximately x magnitude minus n dot r of t prime. So n dot r of t prime is the following. N dot r of t prime is the following. N is the location of point of interest n hat, and r of t prime is the location of the charge. So suppose that the charge is moving around somewhere, is localized, and if you are looking at the charge is radiation at very far field, you can do the same tricks we did in the radiation the far field zone. That was nothing but the x minus x prime magnitude is equal to, from the Taylor expansion or binomial expansion, x magnitude minus the projection of the x prime along the n hat. Okay, so same trick. Okay, so basically the form of the expression takes the following form. A of omega Fourier transform of the A will be a square over 8 pi square over c 1 over 2 minus infinity to plus infinity e to the I omega t prime, and for r, which is equal to x minus x prime, I can write what? Let me take this term here first, and dot r of t prime, and the rest of the expression is n cross n minus beta cross beta dot divided by 1 minus beta dot n. This should be square because this was cube here, that is square. And there's one factor here, e to the I omega x. I take this term outside, okay? I omega x, omega and x are constants. X is the location of the interest. The changing parameter is what? X prime. The location of the charge is changing, x prime or r, x prime or r. Or let us call, yes, r of t prime. Basically, when you eventually you will need the what? Absolute square of this. When you take the absolute square of this phase factor will be 0. Okay, it will not be contribute. So if you are clear at this point, I will put the expression quickly in a compact form, and next time we will do the application. So are you clear with the derivation steps? So Fourier transform of the field we are calculating, r is cancelled, and instead of dt we write 1 minus beta dot n dt prime, so one of the factors is cancelled. Then since we are looking at the radiation in the far field zone, we said that x minus x prime approximately x minus n dot r, and we put in that form. So let us continue to do calculations. So this is just a phase factor. Now, so far we write everything in terms of the t prime. T prime is the location of the charge. This is the prime. But this is, if you look at here, where is the integration element dt prime? So since the limits are minus infinity plus infinity, you can recall the t prime as t again. So this is a dummy integration parameter. I will call as a t, and so let us call as a t prime as t, just due to the integration parameter. And there is another thing, tool. This in the part of this integrand, n cross n minus beta cross beta dot over 1 minus beta dot n square could be written as the derivative, time derivative of this quantity. Minus beta dot n. This is one other thing. So as I said that eventually you need the square of the absolute square of this. You don't need the phase factor e to the I omega x. So that integral could be written in the following form. I of omega could be written as e square over 8 pi square c 1/2 dt e to the I omega t and that r of t instead of all bunch of this n cross n minus beta cross beta dot over 1 minus beta dot square, you can write this as a d over dt n cross beta 1 minus beta dot n okay. This whole bunch here is d over dt. If you will dt as a t prime, nothing will be changed. Actually, you can put as a t prime. Okay, nothing will be changed because this is a dummy integration parameter. You can call t as t prime. Nothing will be changed. Then you can apply the integration by parts. So if you call this is a du and so dt times that du, and if you integrate by parts, integration by parts, will bring the following things. Coefficients is the same, e square over 8 pi square c 1/2. So if you call this bunch as a du, then the integral will be what? From minus infinity plus infinity. There was a phase factor here, but I am ignoring this phase factor because eventually we will take the absolute square. So you can ignore that phase factor because it has no contribution of the intensity spectrum. And the integral of this, if you call this a du, integral of this will be n cross beta divided by 1 minus beta dot n. And if you call this a v, you should multiply by dv. What is the dv? If you take the derivative with respect to time, what you are going to obtain? I omega times 1 minus n dot r dot over c times dt. I write the integration by parts. This is du, the integral of this will be, okay? And this is v, let's say. The derivative of this will be what? Oh, exponential e to the I omega t minus n dot r of t n dot r of t, and I think this should be divided by c, and this should be divided by c, and all of them divided by c. y divided by c, because r was x minus n dot r, and we have the what? R over c. Okay, so you can insert r over c. So, and the integral have to be taken through the dt or dt prime, doesn't matter. So what is r dot over c? Beta. So this term is beta. Therefore, this is 1 minus n dot beta. This is divided by 1 minus beta dot n. This will be cancelled. We have the I omega. And you can keep the phase factor or not, it doesn't matter. The final bottom line will be the following. I have the Fourier transform of moving and accelerating charge particle. Then the intensity distribution of per frequency per Solid angle, I know that that is nothing but 2 times magnitude square of the Fourier transform of the A. And if you take the square of that, you will get the following. You have the I omega, that will be omega square, and you should take the square of this, and if you do this, you will obtain the following. So we will take the square of this, so that is 8, 2, 4, that will be the following. E square times omega square divided by 8 times 2, 4, pi square c are the coefficients, and one should evaluate this from minus infinity to plus infinity, n cross beta e to the I omega t n dot r of t over c dt, and take the absolute square of this. So, okay, so this will be the final form of the radiation. So basically we have to know that the beta and r of t and evaluate this. That will give the information about the intensity spectrum. So since I have a time, I can look at the Bremsstrahlung now. So the rest of the part will be the applications. So you can apply this for cyclotron radiation, Cherenkov, Bremsstrahlung emission. Let us look at quickly the Bremsstrahlung emission. So Bremsstrahlung emission is the breaking radiation when the charge enters the medium of the charges. It slows down, makes lots of Coulomb collisions, change of the directions, and lots of curvature radiation. It's very powerful, and it slows down and it emits radiation. Okay, so I think the first, this is proposed by the Tesla, and then the German scientists, I think the Bremsstrahlung is the German word of the breaking radiation basically. So Bremsstrahlung emission, breaking radiation. With the given tools, how we can handle the breaking radiation? That is simple. think about a charge here, and actually you can, this is a quantum mechanical problem, but we are looking at the classical, okay? So you have to draw the Feynman diagrams and work on carefully in generally. If the charge is moving, suppose that this is the another charge. So during the Coulomb interaction between them, this will be slowed down. Some momentum will be transferred to this charge, and this will be lose some charge, and therefore there will be some radiation. So if you call that the impact parameter is beta, B, not beta, the situation is the following. One approximation is the following. When the charge moves, it emits a pulse along the forward direction and another pulse or quanta in vertical direction. These are the fields seen from the rest frame. And we know that these fields, what are these? They are the time-dependent fields. Remember, we derived this when we studied the transformation of the field. So, with respect to the rest observer, the field along the y direction is q gamma b over b square gamma square v square t square, and E1 of t is minus q gamma vt b square plus gamma square v square t square 3 over 2. Remember, we did this in the transformations of the electromagnetic fields. So these are the time-dependent fields. What I have to calculate, I can calculate this one. Not needed this one, they are the same thing. What I have to do, I have to take the Fourier transform of this and to take the square. If you take the Fourier transform, you will have the lots of mathematics, Bessel functions and so on, but the picture is the following. The general picture is the following. The intensity square per Solid angle per frequency will be what? 2 times, let's say let us write for the vertical one, then you have to write that the Fourier transform of the y component, you have to take the Fourier transform of this, and for the x1, x component of the pulse interacting with the charge, you have to evaluate the Fourier transform of the x component. So as I said, this is a complicated stuff, not easy to do in a few minutes, and it requires more time, let's say 1 week. Basically, if you plot that as a function of frequency, the intensity pattern per frequency per Solid angle, you can integrate the Solid angle much more easily, is the following. The second component, which is the perpendicular to the motion, is more dominated. It's flat at a certain frequency, then it drops exponentially. And for the pulse along the motion of the direction is not very important. It is something like this. So this is the contribution of the first one, second one, perpendicular component to the motion, and this one is parallel to the motion, and this is related to each other. If you call this is the total intensity I0, this intensity is suppressed by a factor of gamma square. So basically, when the charge is moving, it will break by the interaction of the another charge, but the basic contribution is coming to the field perpendicular to the motion. Field parallel to the motion doesn't have the effect. So basically, this is a exponential decay. So if you take the integral carefully, find the Bessel functions, look at the asymptotic limits and so on, you will find that this is an exponential limit, and that exponential has somewhere else here decays the function, and basically this decaying is the region of the following. I tell you that if the charge is moving with high speeds, the field lines is something like this, is more perpendicular. And these are the field lines. And if you plot this as a function of time, Vt, so the field, y component of the field, the perpendicular part of the field is 0 at minus Vt when goes to infinity, and plus goes to infinity is 0. Its maximum is somewhere here. And this width is related with the passage time of the relativistic charge particle, and that passage time, delta t, is b over gamma v. If non-relativistic, that is b over gamma v, b over v, but if it is relativistic, the passage time is get narrowed by a factor of gamma due to the length contraction. Basically, you can express the horizontal axis instead of ordinary frequency. You can express a unitless way that you can divide this to the delta t. So that means that this is 1 over time and multiply delta t. Sorry, that will be b over gamma v. B over gamma v is a constant, but this is altogether is unitless. So basically, exponential drop starts around the frequency equal to frequency is equal to what 1 over inverse of the passage time. So this is a detail. Okay, so we are talking about qualitatively doing without doing any calculation. The bottom line is the following. Bremsstrahlung emission is a breaking radiation. When the charge enters to another field, another charge region, it slows down and emits radiation. And our approximation is very simple. We know that the fields, if we think about very simple case, one charge here, another charge here, we know that the field on this charge, it has the x and y component. They are time dependent. We can calculate the Fourier transform and we can plot the intensity spectrum. And that tells us something else. One thing tells us, this is important, the perpendicular component of the field relative to the motion dominated. This piece is okay. And parallel to the motion component is less dominated by a factor of gamma square. If gamma square is high, this is very less. And the frequency spectrum drops exponentially somewhere at which the passage time, at the frequency of the passage time. And the passage time is shrunk by a factor of what? Gamma factor. So in this way, we will look at the other process like a Cherenkov radiation and cyclotron radiation. We will look at the Thomson scattering, and we will look at the radiation reaction force. So this is the one of the processes we look now. So we just look at this piece. For Cherenkov radiation, I will look at this one. And cyclotron one is this one. I will try to calculate the N cross N cross B for the cyclotron radiation. So far we have the qualitative feeling about that what is the intensity spectrum and how we can obtain. As I said earlier, horizontal axis is the frequency. Then you can multiply with the h bar, convert to the energy. So vertical is related with the intensity of the radiation, number of photons given per frequency interval. So observationally, you can observe that the intensity is a function of energy. So in this way, you can compare with the data with the observation, if you have the detectors and so on. So let us stop for today, and the rest of the time we will look at some physical processes. Okay, this was the one Bremsstrahlung emission.